My name is Sri Tulada, and today I will be representing Trijet Limited. We are a small inkjet company specializing on all aspects of inkjet printing. We provide solutions for advanced ink characterizations. We also provide tools to characterize inkjet inks. So the talk today I will be delivering is on advanced inkjet characterization of inks and the jetting predictions. It is important that the ink dynamic properties are matched to the printed and the waveform so that you once get the very reliable inkjet printing. So today in the first half we will cover the fundamentals of ink characterization and how there is a batch-to-batch variation or how subtle changes in the ink dynamic property changes the fluid jetting behavior. And on the second half we will go about showing how this characterization tools can be applied to generate or formulate a reliable inkjet inks. Okay, we will also run a practical course on it, demonstrating how you can see the subtle difference between the inks as a part of the ink characterizations. The training like this is quite important for the inkjet community because if you look at the specification of the printed, most printed have a general bulk property definitions to it specified, whereas in reality we know that the similar ink with a similar bulk property tend to have a very completely different jetting behavior. So the training like this helps people understand the subtle difference and appreciate the dynamic property which is key to inkjet formulations for reliable jetting. And it is very important that as an inkjet community we train the people around the inkjet community the importance of every aspect of the inkjet printing. Inkjet is a multi-physics discipline. It involves chemistry, physics, material science, and waveform. So it's very important that we understand the link between each features of it. So training like this do help people to broaden the skills and appreciate the other side of the story, right? So in order to increase the print frequency, drop velocity, and print reliability, we really have to understand each aspect of the printing behavior, including the fluid characterization, which is a key part in the whole dynamics of the reliable jetting. The benefit for a company like us in collaborating with people and technology like this is to educate, right? Is to make people aware how this interdisciplinary is interlinked together. And this helps us as a community to understand the intricacy of inkjet printing and achieve a much more reliable jetting for the whole community.
Estamos en la jornada técnica de Personas y Tecnología. La verdad es que ha sido súper interesante. Yo lo recomendaría bastante, ¿verdad? Porque la verdad es que te ayuda mucho a comprender el funcionamiento de la tinta con consonancia con la waveform y al final poder sincronizar estas dos partes y sacar el mejor rendimiento de la aplicación y de la tinta.
I think it's really very interesting presentation, really technical. So it helps a lot the ink manufacturers, printhead manufacturers to find or to develop quicker the projects. So it helps a lot on the development of the waveforms. It helps a lot on the ink manufacturers to develop the ink, apply it to the final application of the OEM.
Para mí es una jornada muy interesante porque dentro de las tintas las técnicas de caracterización son muy importantes y es una oportunidad increíble para aprender el funcionamiento del equipo y además en directo.
It is a great opportunity to be here because this area, the Castellan area, is very well known about one of the inkjet center, and then especially for some particular type of ink formulators are focusing on here. But up to now, there are a lot of inkjet conferences in like Cambridge in UK or in Switzerland or Germany and places like that. But I think it's really, really important for us to just give a message to the particular region that I can see a lot of ink formulators actually I haven't really seen before here. Then also the tree. He's the one of the top specialists in the rheology. Is giving a direct lecture of why inkjet is so difficult and what is the reason, and then also how to overcome it. But this is absolutely important. So I'm very much thankful to people in technology for organizing this.
Esta jornada me ha parecido muy interesante porque hemos podido aprender un montón de cosas sobre las waveforms, sobre las propiedades viscoelásticas de los inkjets, y por eso os invito a venir a futuras jornadas de Personas y Tecnología, porque aquí vais a aprender un montón de cosas y vais a conocer un montón de gente en el sector.
Probably the best thing so far has just been the networking, actually bringing people together from different parts of the world, different backgrounds and experiences and capabilities. It's been a phenomenal event for that. So all in all, worth the trip, and would recommend in the future other companies come.
Me ha parecido una jornada muy interesante, además de toda la parte técnica que me pareció muy útil, además, y también me permitió conocer a gente con la que quizás en un futuro pues, podríamos colaborar.
I believe the session of today is super useful also to bring a standard to the industry, because getting this data for the ink manufacturers, OEM and printhead manufacturers will help a lot. So normally projects on bringing products innovation to the market are supported in collaboration, and this data will help for sure in future.
Good morning. Welcome to the 5th training course of the People and Technology Technical Conference. And today I will be demonstrating a 3-jet high frequency rheometer called the TreePab. So this TreePab is one of the high frequency rheometer developed specially for inkjet ink characterizations. So what it consists of here is, you can see that this is the TreePab high frequency rheometer that can carry out the complex rheology of inkjet ink up to tens of kilohertz. So this consists of the TreePab rheometer, the lock-in amplifier to operate this TreePab, and the chiller to control the temperature. Right? So the way it runs the experiment is it characterizes inkjet ink exactly like what it happens in the printed channel. So what we would do, the test is, as I will show you here, we operate in 2 different modes. One, what we call is a standard complex rheology mode, and the next one is the printhead mode to match with the waveform characterization. The first part of it is, I will show you, is how we use this in the traditional complex rheology mode. So what you have it is, we will put a drop of ink here, and we'll do the frequency sweep of it and measure what we call is a complex rheology. And you can see that we can measure the viscosity of the ink, but the viscosity of ink, we can break that into 2 different parts called a viscoelasticity, the viscous part and the elastic part. And this elastic part is the critical part where a subtle difference in the formulations or a batch variation of ink to ink changes. And this is key in terms of the fingerprint of the inkjet ink. So if you want to make a reliable ink, then you really have to control this viscoelastic property of the ink, especially at the high frequency. So let's see how it operates, right? So basically, you have a plate, you have the rheometer, the temperature is controlled here through the software, and let me open it. So as I open it here, so this is, just to open it here. So you see here, we have a small samples. I had a sample before, so let me load a new sample and we see how we will do the test. So in order to run the sample here, let me just do the bit of wipe of it. It's fairly straightforward. And so in order to load the sample, all you need is a small, you can load any inks. So for now, I will load one solution here. All you need is a drop of ink. So you place a drop of ink, and what you do is you set the gap which is closer to the printhead, and here I'm now setting a 20 micron gap here, and all you do is now close the system. And so this basically is pretty much similar to what you have a printhead. The printhead would have ink in between and nozzle would be here. Only what we do is we're blocking the nozzles here with the top plate. And now we'll close this. So we make it almost like a printed ink in a printed channel. And instead of doing the frequency, instead of doing a waveform, what we will be doing is now is the rheology of inkjet ink. So we just tighten it to make it hermetically sealed. Now all I need to do is, if you come to the measurements here, we're running from 10 to tens of kilohertz, and we're just running this 2 measurements, you load the name of the sample and you press the run. As you see, we are now sweeping the frequency as it operates. You can see here that now we're going from 10 Hz. So this will keep ramping up in a frequency sweep all the way to 10 kHz. Because this operates in a same like a printhead in a piezo, it's very quick. So you can do the whole test in less than 2 minutes. So you can see that we are now ramping the frequency. It's measuring the test, it's applying the strain in it, and what we're looking at is the response of the fluid with respect to and the phase shift, how the phase is shifting, whether how close it is in terms of viscoelastic properties, right? You can run it at a different temperature. At the moment we are doing at 25 degrees. The software automatically sets the temperature here, and so that it's green, so the temperature is running it. As now you see that we are almost in 2 kHz, close to 2, and you can see that it's ramping it. As it ramps, we will do the whole measurements, and when the test is finished, you will get the plot like this. So you can see that it's almost finished. So you can see that this test is pretty quick, and it measures the property of ink in the channel. So the experiment is already done. So if I call it ink 2, ink 3, and there. So that you can see that now. You get a plot. This is the complex viscosity, and this is the liquid part of it. What is interesting is even this fluid up to about 800 Hz, this fluid is very Newtonian. But above that, see this elasticity? That's what is the important part. So every ink will have a difference in this elastic behavior, even if the bulk property is the same. So this is as quick as it can get to get you the whole complex rheology profile. This is again the same complex TRIPAB high frequency rheometer. Because this operates same as designed in a way such that it works exactly like a printed mode. So what we have also done is we can also use this as a waveform optimization tools. So what we are going to do here now, instead of using a standard complex rheology mode where we apply the sinusoidal signal, we're going to apply the square signal and see how the fluid would respond to it. So just to give you a background, here it's a blank. There's nothing here in the fluid, and you can see if I operate this in a standard frequency sweep, what you would see here is a new software. It's called the TRIPAB printed mode, where we can do what we call is, instead of doing the frequency sweep, we are now able to do the temperature sweep. So we can put a fluid in it, run across the temperature, and then software will automatically determine at which temperature the ink will work best. What is the pulse width of the fluid it's going to be, or the effective speed of sound, what sort of drive voltage you need for the fluid to jet, and how long you need to wait in terms of so that literally defines what the maximum print frequency of the system. So let me run a test here. For now, for the demo, I will just do one temperature on this. So I set single capture instead of temperature sweep. So I'll set at 25 degrees, and this is the blank without the fluid. And if I press the run here, it will do a step strain analysis. So you'll see the step running it, and then what you will see is the response of the fluid, right? So it's the run, the tester, and what this tells you is, because this is blank here, the speed of sound is very, very high, so the pulse width. But what it also doing, because there's nothing fluid dampening it, you get lots of resonance. Now let's see what happens if I put a fluid in it, right? So what I will do is exactly the same like before. I'll put a drop of fluid, and we will now set this gap to about 100 micron, which is similar to a printed channel. And we will now close this like the same thing I did before, right? We'll make it hermetically sealed, and then let's close this one. So I have now closed it. So what basically this is doing is, this is mimicking exactly what happens when your ink is in the channel, and when you apply the waveform, how the energy would transfer to the fluid and how it ejects. So let's now run the same test. Keep an eye on this. When we had no fluid in it, you had a quite fast, rapid peak, but we have lots of ringing, which is what we call as the meniscus oscillations, right? Now if I have a fluid in it, now this is a fluid here, so let me just call it a ink 1 here. Ink 1, and now let's do the test run. Now keep an eye on this one here, see how it dampens it. You'll see the shift here, and you'll see this dampening much better. Let me run it. And the test is very quick. It takes less than 2 seconds to do it. The test is done. It will now display the plot. You can see that now. It's quite interesting, right? The shift here is because the effective speed of sound of the fluid is much lower than that of the metal. So this distance here literally defines what the pulse width of your waveform has to be. And what this amplitude here, response, tells you what sort of energy it gets at the fluid, which will be related to how much of dry balls you need to put it. But what's more interesting is, because this fluid is slightly more viscoelastic, you can see that it dampens very quickly. So this fluid is much better in terms of having high prane frequency because it has a damping behavior, so it dampens the fluid, right? So just by doing this experiment, we can now measure every features of the ink with respect to the waveform. So typical waveform would take about 2-3 hours to do it. So this is literally taking 2 seconds to do the test. So what we could do now, instead of doing this, we could do the whole temperature sweep. So instead of doing one set, I could literally say, do the temperature sweep here. If I don't know any fluid, so it will do the temperature sweep and tell it to run it, right? So if I tell it to run it, so the ink will now ramp the temperature. So this will now control this fluid, ramp the temperature, and as the temperature increases, it will capture each of this data point, and then based on that, the software will automatically analyze to give you all the peak time for that's related to the pulse width, how much it resonates or the oscillations, and based on that we can literally optimize and determine what is the best temperature for that fluid. So you can see that it will be ramping it. You can see the software has already changed the thermostat temperature to ramp it, and as you increase it, you will see the temperature captures each measurement. So this is how you would do the whole sweep. In a matter of less than 20 minutes, you can do the complete temperature sweep, let's say from 25 to 50 degrees. It takes less than 20 minutes to do the whole test. So it's now changed the setup temperature, and it measures the temperature of the sample here, which is here. So this is the thermostat that controls this temperature, and now when the temperature reaches the right temperature, it does the so when the temperature is right here, which is the sample temperature, so this is the temperature in here, and after that, when the temperature is reached, it measures the property. Thank you, People and Technology, for the invitation. It's been an honor to present here and share some of our understanding on fluid characterizations of it. Thank you very much and enjoy the day.